Good morning, my good students. This is Dr. Eddie Morgan over at Clovis East High School. Today we're going to take our understanding of exponential functions and talk about exponential growth and exponential decay. In other words, exponential functions that are increasing versus exponential functions that are decreasing. We have here, to begin with, some definitions. These are something you can look back at as we go through the lesson. We notice here first exponential growth and exponential decay. The key thing to notice in these two things here is when you're multiplying a number, think about multiplying any number by another number. What can you multiply it by that it gets bigger? Well, it has to be bigger than 1. If you multiply by 1, you get the same number. But if you multiply by 2 or 3, it doubles, it triples, it gets larger. So anytime we're multiplying, in this case, y equals a times b to the x, if b is bigger than 1, this is getting bigger, it's going to grow. On the other hand, decay, you notice the second one, if b is less than 1, between 0 and 1, in other words, it's a fraction like a half or 0.75, something there, half of something means it's getting smaller. And that's the difference, real difference between growth and decay. Is the b bigger than 1 or less than 1? Second, we have growth factor and decay factor. Key thing here is that if something's growing by 3%, the next year is not going to be 3%, it's going to be 100% plus 3%. So that's why we say growth factor is 100% plus the percent rate of change. Likewise, if something's decreasing by 3%, next year it's going to be 100% minus the 3% change. And we'll get into that more as we get into the lesson. So this slide shows the exponential function. The basic form is y equals a times b to the x, where a is the initial amount. It turns out to be the value of the function when x is 0. B is the growth or decay factor. Remember, this is 100% plus or minus the percent rate of change. X is the number of times the growth factor is decayed, and y is the result. Remember how this compares to a linear again? Exponential y equals a times b, but if I look at a linear function y equals mx plus b, you can kind of compare them. First of all, notice that the initial value in the linear function, when x is 0, our y-intercept is b, but in the exponential function, the y-intercept or initial value is a. They both represent, if you look at the diagrams, the value of the function when x is 0. At the same time, how much is it growing? In the linear equation, it keeps going up by m. If you have a slope of 2, it grows by 2 each time. On the other hand, in exponential, it's being multiplied by b. So there's kind of a similarity between these two. When we talk about exponential growth, the key thing there is it's getting bigger. In this case, we're dealing with the initial value being positive. But if our b, a equals b to the x, is greater than 1, then the exponential function is going to be increasing. Consider these examples. Y equals 2 to the x. 2, and then 2 times 2 is 4, 2 times 4 is 8, 2 times 8 is 16. We're getting bigger and bigger because the b, y equals a times b to the x, is greater than 1. Here, 1,000 times 5 to the x. I'm not concerned what a is, 1,000. It just has to be positive. But I keep multiplying it by 5. Each time you multiply 5, it gets larger. And then y equals 600. Notice the fraction. Be careful here. Sometimes people think fraction, oh, it's going to be smaller. But notice this fraction is 4/3, 1 1/3. It's greater than 1. So this is going to be an example of something that is growing, increasing. When we look at exponential decay, the difference is that my b, my factor here, is between 0 and 1. It's less than 1. It's like a half or a third or 3/4, or in decimals, 2,500, 7,500, something of that nature. So in this case, y equals 5/10 to the x. 5/10 is less than 1. So this would be an decaying exponential function. 1,000 times 2,500 to the x. 2,500 is like 1/4. Again, less than 1, so this represents a decaying function. And finally, here's a fraction. This fraction 3/4, however, is less than 1. So 600 times 3/4 is going to be less each time. So in the next set of problems, we want to identify whether the function is exponential growth or exponential decay. Look again at the right of the screen. Remember, what makes it growth is the factor with the exponent. Is that factor a growth factor, meaning that b is greater than 1? Or is it a decay factor, meaning that b is between 0 and 1? That's all we have to do is look at the b. So in the first one, y equals 3 to the x. Notice b is 3. 3 is bigger than 1. So we have exponential growth. This means I keep tripling the number. It keeps getting bigger and bigger. On the second one, y equals 75 hundredths. 75 hundredths is like 3/4. It's between 0 and 1. So in this case, it's going to be exponential decay. I'm reducing it by 3/4 each time. In 3, I have an a there. But notice 3 over half. 3 over half is 1.5. That's bigger than 1. So that means this is exponential growth. Number 4, 3 times 1/4. 1/4 is a fraction that is less than 1. So in this case, we have exponential decay. So now let's look at a couple of word problems, some practical problems. A gym currently has 2,000 members, and it expects to grow 12% per year. How many members will it have in 6 years? All right. So let's consider this. First of all, it has 2,000 members. That's its initial value. So A is going to be 2,000. It's going to grow. So we know our growth factor is going to be bigger than 1, and it's going to grow 12% per year. Now let's put percent into a decimal form. Remember, the percent sign means divide by 100. So 12% is 12 divided by 100, or I can write it as a decimal 0.12. All right. Remember, we said it's growing, so our growth factor is going to be bigger than 1. So it's not going to be 12. It's going to be 100% plus 12%. So and we want to know how many members we'll have in 6 years. So we're trying to find out when x, the exponent, is 6. So here's my basic equation. A is 2,000. B, my growth factor, is the 100% plus the growth rate. So that's 112%, or 1.12. We're looking for this equation when x equals 6. So we plug everything in, and we have y equals 2,000 times 1.12 to the 6. At this point, you're probably going to want to get out your calculator, and you're probably going to once again need to use that exponent button. On most calculators, it's either the caret sign, or your calculator might have an x to the y or a y to the x. So in this case, I would type in my 1.12 and then my exponent key, and then to the 6th power, press equal, and I would find out I would get something like this. 1.112 to the 6 is 1.973822685, and I just cut it off at that point. All right. So generally it's about that much. Usually when you're using your calculator, you just leave this as it is. You won't even round it off, and then you can multiply by 2. By the way, that's a hint of solving these. You don't do 2,000 times 1.12 first and then to the 6th power. Remember PEMDAS? Parentheses, exponents, and then multiply. We do the exponent first, and now we multiply that. And now we're going to round off 2,000 members. It makes sense to round off to the nearest whole person. So I'm going to round off to the 7. I notice over there there's a 6. That is more than 5, so we'll round up and say in 6 years they'll probably have about 3,948 members. In our next problem, the local animal rescue league is trying to reduce the number of stray dogs in the county. They estimate that there are currently 400 stray dogs, and that through their efforts they can place about 8% of the animals each month. How many stray dogs will remain in the county 12 months after the animal control effort is started? So as we look here, we realize what they're trying to do here is reduce. That means they wanted to lower the number of stray dogs, so we're dealing with exponential decay. They're starting with 400 dogs. That's how many dogs they think are strays out in the county. And they think that they can reduce it by 8% each month. So their decay rate is 8%. All right? And they want to find out how many do they think they will have in 12 months. All right. So here's our equation. And we know that the starting point, initial value is 400. What's the decay factor? Well, the decay factor is not 8%. It means that after 1 month, I'll have 100% minus 8%. In other words, my decay factor is 92 hundredths. They want to know how many is it going to be after 12 months, so I let x be 12. And now I can write my equation. Y equals 400 times 92 hundredths to the 12th power. Again, take out your calculator. Remember, the caret or the x to the y or y to the x is the exponent function. So I put in 0.92, whatever button I use for exponents, 12, and I find out that that is about 367 thousandths. And then we multiply that by 400. Now in this case, we're going to round off again to the ones because we're dealing with whole dogs. To the right of the 1 is a 0, that he's less than 5. He doesn't go to school with us. So our answer is, in 12 months, they'll have it down to about 147 stray dogs. So problem 7. When a new baby is born to the Johnsons, the family decides to invest $5,000 in an account that earns 7% interest as a way to start the baby's college fund. If they do not touch that investment for 18 years, how much will be in the college fund? So let's look at the problems and break down and look for the numbers and the key words. First of all, we notice they're going to invest the money. Invest implies that it's going to grow. So we're looking at an exponential growth problem. They started off with $5,000. That's our initial investment. And it's in something that they expect to earn 7% interest. Now this is 7% compounded interest. In other words, it's not just 7% per year, but each year you get, it's not 7% of the original amount, it's 7% of what you've already earned. So you start making interest on interest. And they want to know how much it'll be worth after 18 years. So those are our components. Our equation, y equals a times b to the x. A is our initial value. That's where how much money they put in to begin with. That's $5,000. B is the growth factor. Now notice it is not 7%. It is 100% plus the growth, 107%, or 1.07. Now they want to know how much it'll be in 18 years, so we'll let x equal 18. So there's our equation, y equals 5,000 times 1.07 to the 18th power. You can see at this point, this is where you want to use that exponent button. You don't want to go 1.07 times 1.07 times 1.07 18 times. You could do that, but there's a good chance you might make a mistake along the line. So this is when these calculated keys get really handy. So I'm going to type in 1.07. I'm going to put in whatever my exponent button is, and then the 18, the exponent, and press equal. And you see that equals about 3.379, etc. As the factor. Again, you always do the exponent before the multiplication. We do 1.07 to the 18th, and then we multiply by 5,000. And we get $16,899. And so this time it is cents, so we're going to round off to the cents. So to the right of the 6 is a 1, that's less than 5, so we'll drop that off. And so they can estimate that by the time their daughter gets to college, their $5,000 will have more than tripled, and that will be available for her to use in college. Problem 8 is our last problem today. The population of a city is 45,000 people, and it decreases by 2% each year. If the trend continues, what will the population be after 15 years? So let's look at the important numbers and words. Notice, first of all, decreasing. That tells me we have a decay here. It's going down. Also notice it starts with 45,000, and they expect it to decrease 2% per year. All right? And then how long do they want to project out? They say, let's figure out what it's going to be in 15 years. So here's our equation. A is our initial value, that's 45,000. B is our decay rate. Again, it won't be 2%. It goes down 2% each year, so each year it's 100% minus 2%. So our decay factor is 98% or 98 hundredths. Now they want to make a prediction in 15 years, so we'll let x be 15. So now we put everything in there. Y equals 45,000 times 9800 to the 15. Again, get out our calculator. You're either going to use the caret key, the x to the y key, or the y to the x key. And again, we do the exponent first before the multiplication. So 0.98, exponent key 15, and that equals about 738 thousandths and extra. So now we multiply. Again, it's easier not to round off at that point. Just take your exponent calculation and multiply by 45,000, because now you'll do the round off. And so we're doing people, so we'll round off to the nearest whole number. If I look to the right of 5, there's a 6. That's bigger than 5. So we'll round up to 236. So in 15 years, they expect the population to be down to 33,236 people. All right. It's been a good day. I hope that helps. Keep well and be safe out there.